We're live on YouTube. Okay, if you want, Connor, feel free to share screen already. Ladies and
Yes.
gentlemen, Connor was so kind to do a quick introduction to PINs, physics-informed neural networks, with MATLAB, and he'll walk you through the implementation and training physics-informed neural networks inside of the environment. So the stage is yours.
Thanks very much, Jousef. Yeah, it's great to be with you today. The first thing I need to do is figure out how to share my screen, which is, here we go. Sometimes it's easier said than done, isn't it? All right. Okay. How's that? Okay, we can see something now?
Yes.
Super. Right, so I'm going to try to increase the resolution a little bit so we can see. And then I'm just going to start writing code, and we're going to do this together. So Jousef, you can ask me questions along the way and ask me what I'm doing, and we'll do this kind of interactively, if that sounds good to you.
Sounds great.
Cool.
Yeah. I'm going to have a look in the comment section as well on YouTube and LinkedIn. So if there's any questions from the audience, we'll just take them
Great.
as they come.
Sounds good. All right.
Let's go.
Okay. So yeah, so the goal for today is to get sort of an introduction as to how to build a physics-informed neural network in MATLAB. And so to do that, we're going to take a very simple case and kind of build something up for that very simple case, right? Of course, in a real application, things might be a little bit more complicated in terms of the differential equation or in terms of the data and the domain and so on. But the ideas are the same, and the purpose of today is really to just build code that's kind of demonstrative or illustrative for the whole process, and not to go into too many kind of deep technical details. Okay.
I think that makes sense. One initial question we have, Connor, maybe you can already answer that, is there something like AutoDiff on MATLAB?
Yeah, it's a great question. Yes, absolutely. So within the deep learning toolbox, the MATLAB deep learning toolbox, there's kind of reverse mode AutoDiff capabilities, and that's what I'll be using in order to build the pins today. Yeah, so it's exciting. All right, now the specific simple example I had in mind was the classic mass spring damper system, which is just a simple sort of second order ordinary differential equation, which describes like a mass on a spring with a dashpot or a damper, and we're going to study the dynamics of that system. Okay. And now in order to kind of kick us off, I'd prepared some data that I'm just going to load now, rather than kind of spending a lot of time preparing data, which is kind of fun and a kind of necessary thing to do, of course, whenever you're doing these kinds of applications, but it doesn't get to the meat and bones, of trying to build pins. So let's get started. I'm going to load that data. Let's write like this. Let's say load data, and we'll try and write comments as we go because that's kind of good practice, and it sort of hopefully will deliver some of the intent of what I'm trying to write here. Okay, so what I've got in here is, if I can increase the resolution, hopefully everyone can see. Let me increase the resolution a bit more actually. I'm going to go to fonts. I'm just going to make everything really big. How about that? Oh, something's frozen. Oh, we'll see. Okay. That didn't quite do what I wanted it to do. Let me try that again. Let's see. There we are. Okay, so now things are nice and big. All right, so we've got some constants which correspond to the kind of spring coefficients in our differential equation, k, m, mu. We've got some time domain that we're going to solve our problem over, and we've got some data, and we're going to use that data to kind of train the model. So the first thing we should do is just plot everything to look at the system, get some visual representation of the system. So I have written a function here that will help me plot the data. So let me just call that function. All right. So I'm going to call that and go back to my editor and run again. No, something's gone wrong. Let's see. What did I forget? Okay, not immediately sure why that's gone wrong. Obviously some hiccups in my preparation here because I've got all these variables. Let's just try run that thing again. I'm gonna have to have a look at what's going on in here. So there's something wrong with this solution function. And we must be missing some of the coefficients in that solution function handle. And I would need to regenerate those if I want to plot that. But I'm not sure how to regenerate it. So I'm a bit stuck. It's not a great start. This is the classic kind of issue that we can run into when we're not well prepared, which obviously I'm not today. Let me just take a minute and try to figure out how to move on here. Well, I guess we're just gonna have to try not to plot the solution. Let's see, we'll just plot the other bits. All right, let's try this. Something else has gone wrong now. This must be numeric. I'm really not sure what's going on there because I've passed everything in. Okay, just gonna have to do a bit of debugging.
Probably also good to do it on the fly, Connor.
Yeah. So we're gonna use the debugger. We're gonna call it again. So I've added a breakpoint, so I'm gonna stop here. T-pin. Oh, something's getting passed in the wrong. Did I miss an argument? Is it that simple? Yeah. I just missed an argument. So what I could see was that one of the variables was kind of in the wrong state. I'm going to step out of the debugger. Try run this all again. I can delete my breakpoint now and carry on. And have I got a plot? Maybe. Maybe I can even add this back in. I'm going to close all my plots. And let's get back to we can see the code here. All right. And it worked this time. All I did was get the function signature wrong. Okay, that was fun, wasn't it?
Perfect. Yeah.
So what I wanted to actually show here, eventually, we got there eventually, is um, I've got this exact solution in blue, and now because we're solving a mass spring damper system, we can solve this equation analytically. And so we've got this nice analytic solution in blue. Um, X is the displacement of the mass, and t is the time sort of horizon that we're solving this system over. Now I'm going to solve the pins problem here with a kind of a mixture of data. I'm going to use the kind of underlying true data, and that's like these green circles here correspond to certain time points and certain displacements x that are like true values that I'm going to do supervised learning with. And then also what I'm going to do, or what I've done here, is sample the time domain. So choose some vector of points along the time domain that I'm going to use to apply the pins loss, or the physics informed loss, right, which is the key component to pins that we've discussed before. And the reason I'm setting it up this way is because this is, I think, one of the kind of the best ways to actually go about solving pins problems, right? One of the great things about pins is it gives us the flexibility to solve the equations as we know them, but also add in any observed data that we happen to find, and just mix and match very naturally between those two kind of ways of training a neural network. So this isn't the only way that we can do pins, but this is just how I wanted to set it up for today. So hopefully what this plot that we eventually got to should make clear is that we're solving the problem with these points, the sort of open circles here, and also the pins loss applied at all these like little green dots.
We had one question regarding the loss term. Is there a simple way to balance multiple loss terms in the objective function?
Yeah, we're gonna get onto that. And I think there's lots of different approaches for how you would do it, but we'll just work through that and try to figure that out. Yeah. All right. Okay. So let's get on to the fun stuff now. So let's build the neural network. Okay. We've got our data. Now we want to build a neural network. Okay. And here's how we do that in MATLAB. So we set up a list of layers. Actually, you know what? I'm going to jump the gun a little bit. First of all, we're going to set out some sizes that define this neural network. In particular, the input size, which is going to be 1, the output size, which is also going to be 1, and the number of hidden units, which, let's say 128, nice power of 2. The input size is 1 because the input to this network is just a single time step or time value. And the output is 1 because the output is a scalar displacement, the corresponding displacement x, right? The kind of y-axis on that figure that we were looking at. So that's our sizes. And then once we've got our sizes, we can build a layer array. And this is how we build neural networks in MATLAB, with an input layer. And in this case, we want a feature input layer, which means we're just passing features or vectors into the neural network rather than something higher dimensional tensor like an image. And then we're going to build a multi-layer perceptron, right? So we're going to build a bunch of fully connected layers or dense layers and non-linearities after them. And this is how we do that in MATLAB. So we write fully connected layer, and num hidden units is our hyperparameter for that fully connected layer. And then we choose a non-linearity. I'm going to choose tanh layer, but we could choose other things there if we wanted. Let's have another one of those. Fully connected layers and tanh layers. And then we'll have, at the output, we'll have our final fully connected layer with the appropriate output size. And once we've done that, then we can create our network using the DL network, deep learning network, function constructor. And there we are. And that would need to be layers. And once we've built our network, then we can take a look at it in the deep network designer. So I'll call that And then we can run this code, and I've got a typo there, but it was only a comment typo, so it shouldn't destroy everything like last time. So let's run this section and see what we get. Now, one of the nice things about writing code like this is that it's really easy when you're defining your neural network to just tweak that definition. So if I did want to change the nonlinearity here to something like ReLU layer or swish layer or some other variant of ReLU or sigmoid or whatever our favorite activation function is, it's as simple as me just changing the code there such that it would say, swish layer. Oh, well, I can't type now because something's coming up. Let's see. Okay. So now we get a visual representation in the Deep Network Designer of our network. So we can see that it's a really straightforward linear network with sort of inputs and these kind of fully connected layers in sequence like this. Of course, we can use this app in order to design a more complicated network if we want. I talked about changing the activation function, for example, there. And I talked about doing that with code, but if I wanted to do that, in Deep Network Designer, I can do that. This is more than just a view. So, I could delete the tanh there, and I could add another one here. I'm just adding tanh. I sort of drag and connect, and I can auto arrange it so it looks nice. Another nice thing I can do in this app is to just analyze the network. So this is an important part of building any model for pins or any other applications, because I can just check that the way that the data is being processed inside the model actually conforms and agrees with what I had wanted to do or what I want the model to do. And we'll come to this a little bit later, but we can see that I get a picture here of each layer, what its layer type is, what's the activation size at that layer, and whether the layer has learnables and states and so on. Okay. Now this activation size is kind of important as well, because deep learning is kind of, as a domain, it deals with higher order kind of tensors or matrices. And in our framework, we assign named dimensions to those tensors so that each layer is kind of better able to figure out what's the right way to operate on the data. And the data here is what we'd call tabular data, which means that one dimension is a channel dimension, as we call it, which means like it's kind of an unordered vector of information, and the other is a batch dimension. So every batched observation is kind of independent. Now these labels will come in important later when we actually try to train the network. Okay. All right.
Where would just the output be in this case, Connor?
Yeah, so the output is simply the last, the output that we get from the last layer, which is back to 1 by b after having transformed it internally to like our num hidden units 200.
I was just wondering, because we see the input but we don't see the output at the very end. So I thought it was the naming convention was output, but it's not the case, right?
No, so yeah, we just you can have any multiple outputs of a neural network. So if I wanted to, I could specify the output names to be, say, this final fully connected layer, but also the tanh layer, and then I'd get two outputs. Okay. So outputs are somehow more flexible than inputs. Okay. All right. Now we've built our network. The next thing we get to do is train it. Okay. So let's take a look at how do we do that now. Train the neural network. Okay. So we're going to train it using the Atom optimizer, and we're gonna write the training loop now. Okay. So in order to write that training loop, I need to kind of specify some of the training parameters that I need to kind of declare in order to actually train the model. Okay. So let's start by doing that. Let's specify the training hyperparameters, if I can spell that correctly. Now, the most important one is the number of iterations. And why don't we start with something like 1,000? Now, if this was a batched training, then we'd need to think about epochs, which is the total number of passes over the data, and mini batch sizes and so on, which is how we chunk up our data. But since we were dealing with a small problem here, we're not gonna do any mini batching and just train on all the data in one gulp. So it's a little bit simpler in this situation, but that's one way in which you could sort of extend things. There are some hyperparameters that are kind of specific to the optimizer. And the optimizer that we want to use here is the atom stochastic gradient descent. So let's specify the atom hyperparameters. So we want to specify a learn rate, like an initial learn rate. We can start with something like 0.01. And then atom has kind of two specific parameters that we need to initialize. I don't want to get too much into the details of the atom optimizer, but there's a kind of momentum term and a kind of variance term, or a mean term and a variance term. So we'll call that M for mean and V for variance, and we'll just initialize them to be something empty right now. Okay. Then what we want to do is prepare the data for training. And this is where we dip our toe initially into the world of automatic differentiation. Now, automatic differentiation in MATLAB, in the deep learning toolbox, is handled via something called a DL array. You can think of that as like a deep learning array. And that's the engine which we use to actually track and perform the automatic differentiation that we need to do for training neural networks, in particular things like pins, right? So what we're going to do now is just cast our data to DL array so that it's ready to be used in the training for this purpose. Okay, so our data here is T data, which corresponds to the data, those open circles and the time points at those open circles. Okay, so we have also X data, DL array, X data, CB, and we had the T pins, which is the times that we're going to apply the pins loss. Okay, so I'm going to cast that to DL array as well. And you see here that when I've created these DL arrays, I've done so with the 4 dimension labels, the CB, that we could see earlier when we were analyzing the network. And this is just a way of communicating to the network what the dimensions of the data actually mean, okay? Rather than that have to be sort of understood by convention. All right, so now we've got our data. And we can get started right in the training loop now. So we can do for let's say for iteration equals 1 to num iterations, I think I called it. So we're going to loop over this number of iterations. Now the key components to training a neural network are to compute the loss. For some loss function, which we'll get to in a wee moment, we compute the loss and the gradients with respect to that loss. So we're going to do loss gradients. And in order to compute the loss, and the gradients with respect to that loss, that's where we actually invoke the automatic differentiation, the autodiff. And to do that in MATLAB, we call dl-feval, which is a lot like the feval function, which is a kind of core MATLAB feature. It's a way of evaluating a function handle, a way of evaluating a function. But now we're doing it in a special way that allows us to compute gradients. All right, and the function handle that we want to evaluate, let's call it model loss. We haven't defined that yet. We're going to define that in a wee moment. And it's going to take a bunch of arguments like the network, the T data and the X data. It'll need to take the T pins as well. And it'll also need to take the coefficients of the differential equation that governs this whole thing, which I've added here just for sort of ease of parameterization. So I can kind of change those if I want to play around with this. Okay. Now, for the moment, I'm going to leave model loss undefined. We'll come back to that and we'll define that in a wee moment. Let's finish this for loop first. So once we compute the loss and then compute the gradients with respect to that loss, we need to actually update the model. Okay. And to do that in MATLAB looks something like this. So we say that the network, which is our model, and those kind of atom training parameters, MP and VP, I called them, have to be updated by the atom update rule, which is just this simple function here. And I've got nice autocomplete, which is going to help me get the right arguments in here and not make a mistake like I did earlier. So I want the network because that contains the parameters that I want to update, the gradients that I've just computed from autodiff, these MP and VP arguments, and the iteration that I'm currently working at because Atom is actually sensitive to the iteration, and the learn rate. And there's other parameters, additional ones that are not required for this update rule that I can set if I want a little bit more control. But we're just going to do it like this for now. And that's the key ingredients now, okay, for training the network. So once we've run this for loop, we're done. But we do need to define that model loss function, right? And that's really where we're going to see pins actually, you know, the kind of exciting bit of pins. This is where it all lives, in that model loss, okay? So let's define that now as a loss function, okay? So we want a function that returns the loss and the gradients, model loss, and we want our model loss to accept the network, our kind of observed data, the pins points, the time points that we're going to apply the loss, and the coefficients of the underlying differential equation. Okay. Now, what's this function going to look like? Well, the spirit of what this function is going to do is it's going to take our network, it's going to evaluate two different losses, and we're going to combine them in a sum, and then we're going to compute the total grade, the gradients based on that kind of total loss. Okay. So what I mean by that is that we're going to compute, let's compute the pins loss first. I'll call it loss pin. And I'm going to introduce a new function that I haven't defined yet, just so that I can break things off and make things nice and readable, called pins loss, which is going to take our network, our pins points, and those coefficients that define the equation. Then we're going to compute our data loss, and we'll do the same thing. We'll put that off into another subfunction that we'll define below, and that's going to take our network, our data points. Okay. And our total loss, as I say, is just a combination of these things. And here's where, you know, we talked earlier, Jousef, about how easy is it, or how do we combine different elements of the loss function when we're training pins. This is where we do it. This is the point where we start to do that. And it's you know, there are different strategies for how you would do that, but it's as simple as sort of adding weighting factors like this, which of course you can parameterize into kind of weighting variables. But you know, maybe we anticipate that the data loss is going to somehow dominate. So we'd want to downweight that in some way. I don't know, something like that maybe. Now we're nearly done. You see that I'm getting some mlint here on the gradients variable because I haven't defined it and returned it yet. So the software sort of helped me out here, telling me, hey, Connor, you need to define this variable. So what we can do is we can write gradients equals DL gradient. Now this is again appealing to that autodiff engine in MATLAB. This is how we compute gradients using autodiff in MATLAB. We use the DL gradient function. The gradient of the parameter with respect to the loss, and the parameters here are the learnables inside our network, right? And that net.learnables is how I access those learnables inside the network. All right. So I'm nearly done. Now I just need to define these two functions that I'm going to use to actually compute these losses. Okay. So let's start with the pins loss. So we want net, we want some times, we want these coefficients that I keep carrying around. All right. So now we're really getting to the really fun bit, the bit that this is all about, which is about pins. Okay. How do I compute pins loss in MATLAB? Well, here's how we do it. So first of all, I take my network and I compute some prediction X based on the input data T. So, you know, I went to this these sort of pains to kind of display right at the start that we're computing pins losses over a bunch of time points. So that's my T here. And my model prediction X is you know, what the model thinks that the underlying displacement is, or the model displacement is, based on those time points. And we're going to use that to compute the derivatives so that we can impose our differential equation. And let's do something like this. Let's say actually that what we want to compute is a residual of the equation that we want to impose, which is going to look like m dot the second derivative of x, which I'll call xtt, plus mu dot the first derivative x, which I'll call xt, plus k times x itself. Right, so you can imagine that this stuff on the right hand side, I want that to be 0. Okay, so I'm going to compute a residual term that I want to drive towards 0. And the loss, you know, in order to actually drive that term to 0, I'm going to square it and take the mean. And so I can do that in MATLAB as follows. Use the mean function, use the square, and just tell the software to take the mean over all the elements in there. Now, if we had more complex residuals, we could sort of write that loss down in different ways. But this is kind of a very simple way. Now, as I'm looking at this code, I realize I've missed a star in there to do some multiplication, so I'll just add that in. Okay, but now the last thing for me to do is to actually compute these derivatives xt and xtt, the first and second derivative of the output. So let's do that now. So we're going to use that DL gradient function that I talked about before. We're going to compute now the gradient of the output x with respect to time. So x with respect to t. And I'm going to add a name value pair here just to say, just my way of telling the system, hey, actually, I want higher order gradients here. I'm going to do higher order derivatives. Because often in deep learning, you're only interested in the first derivative. For sort of standard supervised learning problems, we're only interested in the first derivative of some loss, maybe cross entropy loss, with respect to the model parameters. But in this instance, we're interested in higher order derivatives, okay? So I'm just telling the software that. And once I've got xt, I can use xt to define the second derivative, xtt. And you can almost guess what this looks like. I've got xt with respect to t, and that's it. Now, with autodiff systems, we can compute gradients with respect to a scalar loss only. That's kind of how the reverse mode autodiff systems are defined. What that means is I need this first argument here to be a scalar. But as it is, x is not a scalar because it has a c dimension, which is 1, which would give me scalar, but it has a batch dimension, remember that b dimension, which is not 1 because of all the time points that I'm training over. But since each of those time points are independent, if we think back to our days studying calculus, we can just sum all those things up and we're going to get the right derivatives because they're independent. And the derivative at each point is not dependent on the derivative at another point, another batch. So what I can do is write sum over all here and do the same down here so that I make sure that I've got a scalar that I can compute derivatives against. Okay, and that is my pins loss. So you see, it's only a couple of lines of code. It's pretty faithful to the underlying mathematics of the process, which I like. and I've got a lot of flexibility to compute this residual and minimize over it in whatever way I want to. Now we're nearly done. We just now have to fill in that data loss, okay? I think I called it data loss. Let's check. Yeah, got my screen there to help me out. Okay, so my data loss takes net, it takes some input t, and it has some x target. I'll call it like the true x. And this function is going to look very similar to the one above. I'm going to compute some model prediction on the network that I'll call x. And then the loss is simply like an L2 loss, which is like mean squared error of x, and the target's x target. And that is it. And so now we have all the kind of building blocks, the base building blocks we need to actually train a pins model. So we can try this out. We can run this code. Sorry for the scrolling, and we can see if it works. So let's see. So I've already got my network. So all I need to do now is just run this section. So let's do that. Let's see. Okay. So I see that MATLAB is busy, which means this is running, which is good. But I'm not seeing anything about the training process right now. I have no way of really understanding what's happening in terms of the training. And of course, when we're really doing deep learning, we want to be able to evaluate those kinds of things. So I can see now that the training is finished. I've got a new network now, but I don't really know how it's performed. I don't really know what the solution looks like. The only thing I can do is have a look at the loss, which is being kind of updated on each iteration here. So if we look at that in the command window, I can see that first of all, that it's a DL array, just like those DL arrays that I created earlier. So we know the autodiff has been invoked here. I can look at its value and see that it's kind of small, but I have no idea what that really means and how representative that is in terms of the fit. So if we want to look at those things, which of course we do, right? We'll need to do a little bit of tweaking here. And, you know, I kind of just want to make the point, there's the full flexibility here to make and tweak all these things as I like, right? And of course, there's a couple of tools that we can use in order to help. We don't need to sort of build all our plots totally from scratch. So let's first add a way to track the evolution of that loss value as the training is happening. All right. And let's call this create training progress plot. Okay. Now to do that, I'm going to create something called a monitor object. Training progress monitor. And this is a way of just building one of those plots that you're going to use during training, to which you can add all the kind of hyperparameter information that you're interested in. So in particular for us, we can add a bunch of metrics that we want to track during the training process. Now the primary one that we'd want to track would be the loss, right? But for this particular application, I think it's good practice actually to track not only the total loss, which we'll just call loss, but also those individual components of the loss. Because remember, our total loss is a sum, actually a weighted sum of the pins loss, what I call the pins loss, and the data loss. And of course, in other applications, there could be other components in there too. We could have initial loss based on initial conditions, loss based on other governing equations. And right back to that question you asked me at the start, Jousef, about how do I combine these things? I think it's good practice to actually look at the values that you're computing, and then you can decide what's the best way to weight them, right? So we're going to track loss pin and loss data, let's call it. Okay, so we're going to add these metrics to the plot. Right. Let me close that off. But in order to do that, I'm going to actually need some way of computing these things. But of course, I am actually computing them inside this model loss function. So what I'm going to do is just going to update the code here so that I can pull out the pins loss and the data loss so that I then have access to them for plotting. So I think I called it loss pin. Let's just call it like that, and loss data. So let's go and update the model loss function here. All we need to do is say, okay, as well as returning me loss and gradients, let's return loss pin and loss data. Okay. And then what we can do is go back to our training loop. Let's get a bit more real estate here. And we're going to update the monitor using the record metrics function, I think it's called. And we're going to say that loss is equal to, actually, I think we need to tell it the iteration. And then we're going to say that loss is equal to the loss, and loss pin is equal to loss pin. And finally, loss data is equal to loss data. All right. So let's test whether this works. Possibly I've made another mistake here. So let's lower the number of iterations so things run quickly. And run this section again. And what we should see is our training progress plot come up. So I'm just doing this now just to check that I haven't made a terrible mistake somewhere. And it looks like I haven't. So I've got my 3 loss curves now. Everything seems to be looking good. Okay. And then I think the final thing that we'd want to do is actually plot the prediction. Okay. Because I think it's very easy in deep learning to be kind of fooled by metrics. But you can never be too careful. And it's really good practice to plot some examples of the solution that you're actually generating as kind of reassurance that the model is behaving in a way that you really expect or that you really want it to. And in order to do that, I've got one of these functions that I've kind of pre-written since I didn't want to get stuck into the weeds of plotting code. So somewhat at my own risk, I'm going to try to invoke one of those plotting functions now, just to give a sort of sketch of how you might do it in the real world, right? Now, you wouldn't want to plot your solution kind of at every iteration, or at least for such a fast-running kind of training process like this one, you wouldn't want to do that. You typically only do that every some number of iterations. Equally, if you were sort of computing validation statistics or something like that to sort of check for overfitting while you're training, you wouldn't do that on every iteration. You would save some compute time by doing it sort of every so often. And so to do that, I might write some code like this. I might say, well, if the remainder of iteration, and I don't know, let's say some 500 time steps is equal to 0, then in this situation, let's plot something. And we can generate some test data just to test against. Let's just do some random data that's, I don't know, 1 to some 100 points. We're going to need to scale it by the maximum time. We can then get our network and make a prediction. This is the network that we're training right now. And then we're just going to plot that. So plot, I want to do plot model predictions. And I'll try to get the inputs right this time. Oh, so I need a figure. I'm going to need some some testing data, some real data to check against, some predictions, and the iteration. Okay, which means I need to generate some real data, which I can use my function handle for, my solution function handle, which is something I loaded earlier. And I need a figure handle, which I'm gonna create up here. And we can turn it off to begin with. All right. Okay, so let's try this again. And now we should see some solutions being plotted. Not sure where they went, so let's try. Maybe my sub function didn't turn the visibility back on, so let's try it again. This is real, really truly live coding here with all the sort of warts and all. I know I set this to plot only every 500 iterations, but the training is only running for 100, so that's why we're not seeing any plots. So let's see if we see one now. No, looks like I've got another error. Some issue with sizes. Okay. Looks like I got my dimensions wrong here. Oh, and maybe I also want to sort this so that things plot nicely. Let's try again. We'll try one last time. And we'll see how we go. Yeah, there we go. So here we can see we've got our kind of real solution, and we see what the model's doing, and it doesn't look like it's doing terribly well right now. So all right, let's try to train this in anger now. Okay. So what we'll do, we're going to train for a lot more iterations. Let's try something like 5,000. We're also going to try to speed things up. So one last little thing we can do is accelerate the model loss. Now this is a kind of a nice feature that we have that just speeds up the gradient computation process for certain situations. So if the loss function doesn't have any kind of control flow, like any if statements or so on, that kind of thing, then we can what we can do is kind of freeze and save the computational trace, which is a way of just speeding things up, right? So if we say acceleration function is equal to dl accelerate is the function I want of our model loss, and then we're going to use that accelerated function here when we compute gradients. This will just give us a little bit of a speed boost, which we can do now that we're happy with our training loop is doing roughly the right thing. Now we can start to do that. So why don't we regenerate the network so that we're starting from scratch? We don't need to run Deep Network Designer anymore, so I'm just going to comment that out. And we'll run from here towards the end. Let's see what happens. Okay, so we're training. We can see how the solution's evolving over time, so that's good. Our losses have gone way to 0. So that's also good. And we can see that as we're training, we're sort of getting better and better fit. And our hope would be that as we continue that training process, we'll sort of slowly converge, or slowly or quickly converge to the right thing, which, as you can see, it's kind of getting better and better here as we go along.
Yeah, I have one question also with regards to time. Maybe we can, maybe you can answer some of the comments on LinkedIn after the session.
Sure.
Is, let's say we don't have an analytical solution, the exact solution available through a differential equation, for example. We have a much more complex system. How would we build the loss function then?
Right. That's a great question. Let me just stop this, and we can talk about that. So, well, the nice thing about the pins loss component is that it's completely unsupervised, right? So if we look into the pins loss, there's no analytic solution required here. There's no data required here. It's completely unsupervised. So we can carry on training. Then I guess there's the question of how do we compare the solution? What do we compare it against? And that becomes harder. It becomes harder, and you need to think of other ways that you can kind of validate and be sure to yourself that you're getting a solution that's either physical or reasonable or sensible, and so
That
on.
makes sense.
Yep.
That makes sense. That was amazing, Connor. One question is, could you make this publicly accessible so people can actually check it out themselves? Like
Yes.
the code itself?
Yes, that's I'd like to do that. So let me find a way to attach and share this this script that we've just built up and some of these supporting functions, so that people can try it out.
Perfect.
Yep.
This is amazing. Any closing remarks from your side? Otherwise, we'll wrap it up. And I'm sure you also have some other meetings today, so we don't want to hold you up for too long.
Sure. No, thanks very much for spending the time with me here, Jousef. So, it's just really great to dive into pins and to continue our conversation from last time, and really get into the weeds now about how we actually do this. And I hope that today has kind of shown that this is something that's within reach for anyone with a little bit of MATLAB experience, and a little bit of like engineering experience or mathematical experience to do, right? Anyone can dive into this. It's pretty simple to get yourself started. You're always going to make mistakes. We saw me make mistakes today, and that's fine. The environment here is nice and friendly, and it helps you figure out and get through and get something that works.
Amazing, Connor. Thank you so much. Please send me all the relevant links so people can check out some additional information. I think there is some stuff in the documentation people can read about to build their own pins.
That's right.
So yeah, we'll provide you with everything needed.
Super.
Perfect. Thank you so much,
All right.
Connor.
Thanks again, Jousef. See you.